Okay, let's start with the second part of the parallel session on stability analysis of dynamical systems and applications. The first speaker of this session is David Martín de Diego from the Institute of Mathematical Sciences in Madrid, Spain, and he will talk about geometric integration of mechanical systems and applications to optimal control.
Thank you very much, Leo, and all the organizers for this nice meeting. It's important to know people working in related fields, but not exactly the same that you. And then I will try to explain this thing easily for all the audience, I suppose. The topic is geometric integration, is preservation of some geometrical structure in numerical analysis for some system. In particular, I will study, for simplicity, Hamiltonian systems, and also perhaps an application to optimal control. The idea, I will start with the motivation. We can working in a manifold, typically Q, and the cotangent bundle, which is the space of positions and momenta. And this is a very interesting space. It's a vector bundle, takes T star Q over Q. It has a vector structure in all the fibers. And also this is a space geometrically quite interesting because it's equipped with a canonical symplectic structure. This is very important in the qualitative behavior of the Hamiltonian system. This is this omega Q, is the differential of the Liouville 4 or minus the differential depending of the convention. And this is more or less in coordinates. If you want QI and PI, you have this kind of expressions. Now this is the typical symplectic structure that this space is equipped. Now, if we have a function h, which is the Hamiltonian, we have this equation. This is an intrinsic equation that in coordinates gives us the typically Hamilton equation. This is the Hamilton equations. And then it's important, and this is a very special dynamical system, quite important, of course. And one of the properties of this system is it's easily to prove using this expression that this is the preservation of energy. No? The energy is preserved. This is something that we have. You have like a foliation for the energy levels of the integral curves of this Hamiltonian vector field. And we have also another property is the preservation of the symplectic form. We can express in terms of differential geometry in this way, but if you would know is the preservation of this is a mistake, is omega Q. This is the preservation of the symplectic form by the flow of the Hamiltonian vector field. And this is something important. You imagine that we are working in a two-dimensional space. We have preservation of area in this case. And as a consequence, we have preservation of the volume that is different on this contracting metrics that we presented before because they are contracting also the volume. Here, no, we have preservation of the volume. Also, we have some symmetries and constants of the motion, but I don't want to enter here. The idea is to design numerical methods for instance, this Hamiltonian vector field, preserving something that is quite important, the configuration manifold. Q, in principle, is not a Euclidean space, it's a nonlinear space. And then we need to preserve also this structure, and this is not easy. It's also a typical problem in optimization. And also, in this talk, I will concentrate myself to the preservation of the canonical symplectic form. Also, it's possible to study, to preserve also the Hamiltonian, etc. But in this talk, I will concentrate myself on these two problems. The idea, this is the idea to the first part of my talk. This is I will talk about retraction maps, which is a typical tool that appears in many fields in optimization when we are optimizing a function, trying to find a minimum of function in a nonlinear space. Typically, people use retraction map, but also in interpolation theory, etc., etc. It appears in many fields. And here we will present this. Retraction map is also a tool for constructing numerical integrators, but we will use this retraction map, but thinking in the system that we have a system defined on the cotangent bundle, and then the idea is to lift our retraction map to the cotangent bundle, if you want, to the cotangent bundle setting where the vector field that we have is defined on the cotangent bundle. And then we will use how to construct geometric integrators using these retraction maps. Well, first, we start with this, in this menu with retraction map. This is a well-known concept that, for instance, appears in this book by Apsil, Mahoney, and Sepulcre more than 10 years ago. And this is the retraction map on a manifold M. Is a smooth map verifying these two properties. No, the applied to the zero vector is precisely the initial point where is posed this zero in the fiber. And also we have this rigidity property, which is the differential of the Jacobian of the retraction map at the X applied to the vector 0 is exactly the identity map. The typical example appears in the previous talk, more or less. It is this the example of Riemannian manifold. Precisely the exponential map associated to a Riemannian manifold is a typical example of a retraction. These two properties are exactly like we are reproducing the behavior of the exponential map for a Riemannian metric. And this is the situation where this gamma is precisely the unique locally Riemannian geodesic satisfying the initial conditions. And this is precisely the example, typical example, but it's working on manifolds is difficult to find this exponential map. And then perhaps in some cases it's important to find another type of maps which are not exactly the Riemannian geodesics, to find the Riemannian geodesic that perhaps is quite difficult. A notion that this is also important, that perhaps is in some sense interesting for the case of construction of numerical integrator, is this extended retraction map, which is now a map from the tangent bundle, not only of a fiber, to two copies of the manifold M. And this is the funny thing. We do two maps verifying some natural properties, which are this one, and this one is like the previous one. This rigidity condition is also weighted in these terms. Perhaps this difficult to understand why the meaning of these conditions, but also we have that this map is a local diffeomorphism here. It's possible to prove by using these two properties that this is a local diffeomorphism. And this is a property interesting. If you find in Euclidean vector space with the flat metric, you find exactly the typical examples. The explicit Euler method is given by this retraction, which is we take the initial point is the same, and we take this step with the new point is x plus v. But this is an example of typical retraction. That is an example of the midpoint rule, which is given in this way, or these theta methods. And you can find this retraction map in working a manifold. More interesting example, for instance, is the case when we have a exponential map of a Riemannian metric. We can take this kind of retractions, and this is using the projection, for instance, in the sphere, which is also an interesting example. We can find using the projection this retraction map for the extended retraction map for the projection. Okay, this is an example, but the goal here is to obtain retractions not here, not on the manifold, but on the cotangent and cotangent bundle for mechanical systems and optimal control theory. And this is perhaps interesting because we are using all the geometry related with tangent and cotangent bundles. And this is something for us is quite interesting. And that's the idea. I will start in 1 second the tangent leaf of the extended retraction map. Then the idea is to find, we have, instead of, we are looking for a retraction of this type from TTQ now to TQ times TQ. No, this is the lift. No? We have the retraction in principle of TQ, and this is like a retraction on the tangent bundle. For a vector field defined on tangent bundle, this is my question first with second order differential equations. But here we need to use using the double vector bundle structure of the TTQ, this tangent of the tangent bundle, we have this canonical involution, and the construction of a retraction, the lift of the retraction is quite simple. We take the retraction here, and then we take the tangent map of this retraction, but we use also this canonical involution, and this map is an extended, it's a retraction, if you want to, extended retraction is a retraction also on the tangent bundle. And this is also used to construct many numerical methods for this kind of system. But I don't have time to work there for second order differential equations. But we need also to, for Hamiltonian system, remember that a Hamiltonian vector field is defined on the cotangent bundle. And then we need this notion of cotangent leaf of retraction map or extended retraction map. And this is the idea is also using some tools that appears in books of differential geometry, of geometric mechanics, which is the cotangent leaf of a diffeomorphism. We have a diffeomorphism, automatically we can construct this diffeomorphism, we can construct this map here that is possible to construct taking this dual of the tangent of the inverse map. And also we have some construction which is due from Tulchijev many years ago, 50 years ago at least, which is this canonical symplectomorphism, which is changing the, well, I don't want to enter into the details, but there is this symplectomorphism between these two manifolds. This is clear symplectic manifold, and this is also a symplectic manifold using the tangent leaf for the symplectic form, but I don't want to enter here. And also this, well, this is very simple symplectomorphism here, and then we want to define a retraction in this space. This is precisely the space that we want to define a retraction to define numerical methods preserving the structure. Well, this is the construction here. This is the retraction. We take this, Tulchijev symplectomorphism. We take also this thing, which is the lift of the retraction map, and also we take this map, which is also a symplectomorphism. But this is something, a point which is quite interesting. This map is a symplectomorphism. The cotangent leaf of a diffeomorphism is also a symplectomorphism, and also this map is a symplectomorphism. Then automatically, for free, we have that this map is a symplectomorphism. This map here. This is the corollary here, because everything is a symplectomorphism. The composition is also a symplectomorphism. This is that duality between both leaves, but it's not important. But here, this is perhaps difficult to construct, but here appear the construction if you want working with Jacobian of these different mappings here. You can find exactly the definition of everything. As simple examples, if we have this retraction, which is the middle point retraction, we can find the tangent leaf and the cotangent leaf in this simple way. Okay, and this is, and then the idea is how to construct geometric integrator using this retraction map. I have at least 3 minutes. For a Hamiltonian map, remember we have this vector field, which is presented before at the beginning, and then we can construct this thing. Perhaps it's difficult to understand. We have the Hamiltonian vector field, and here we are using the retraction map here, as you see. And this I will explain in a minute better. But this is exactly a discrete equation. You imagine that you have QK and PK, and you can obtain implicitly this QK plus 1, PK plus 1. This is, and automatically by construction is a symplectic map. There is many ways to present this thing. Here I will explain here in this slide. In this slide is perhaps more simple to understand. We have the differential of H here is a map from the cotangent bundle of the cotangent bundle, and using the symplectic form, we obtain the Hamiltonian vector field, and then it's only necessary to produce. We have automatically here a Lagrangian submanifold. I don't want to enter into the details, but here we also define a Lagrangian submanifold, and this is precisely the numerical method. You have a Lagrangian submanifold of this map, of this space. Automatically you have a symplectic method that this is the one that appears in this equation here. This is exactly this equation, but this is simple to compose with this lift of inverse lift of the retraction map. And this is exactly, for instance, if you want, by using this very simple retraction map, we obtain the lift is this one, and this is the inverse of this, and we obtain an explicit symplectic method with this method, which is typical, appears in many books, but this is a consequence of taking precisely this retraction map. And this is, for instance, a more involved example, working with a Hamiltonian vector field in the cotangent space of the sphere. We can also apply exactly the same technique using the projection here, and we can compute, and we obtain a method without using holonomic constraints and nothing similar. We obtain a method which is automatically symplectic, working on the cotangent space of the sphere. And I finish, I promise, Leo, which is, we are working now in the case of optimal control theory. And well, you can think optimal control theory at, well, a very simple way in a minimization of a functional subjected to this control equation. Now we have a control system, and we want to extremize some functional, which is, I don't know, the consumption of fuel consumption or whatever. And then, well, applying Pontryagin-Hamiltonian principle, we have this Hamiltonian, which is a Hamiltonian depending also on the control function, and we have the Pontryagin maximum principle that it also appears this condition here. But we can use also exactly the same scheme to work with optimal control theory and other theories that I will be presenting in a second, which is it's possible to see that the Hamiltonian of the Pontryagin Hamiltonian is like a Morse family of generating function for this Lagrangian submanifold. And then we have this Lagrangian submanifold that is given the information of the optimal control problem. And then I close my eyes and I apply the method. I move to the tangent bundle, and then I move here, and I obtain here a numerical method that automatically is symplectic method also for this optimal control problem. And the extension is also possible for force system, but we are losing, of course, the symplecticity, but it's interesting for constraint system, holonomic system, control systems, and also it's interesting also for reduced system like the rigid bodies, etc. And also it's interesting to use the notion that appears also in optimality, which is a higher order retraction maps and higher order Lagrangian system that is also interesting in optimal control. But it's, well, also it's possible to work with discrete gradient methods, and then to study the meaning of the symplecticity there is also interesting in comparison with other methods. And, well, extension to other situations that, well, we are interested for this port Hamiltonian system, then appear the geometric integration of Dirac system. And I think that all this theory, unless this geometrical framework is useful for this theory. And thank you. I think that I am finishing 2 minutes later, but it's okay. Thank you very much.
Thank you, David, for the talk. I don't know if someone has any question or comment. Maybe how hard it is to extend this framework to reduce systems to work, for instance, symplectic methods for rigid body dynamics or liposon systems?
Well, it's necessary to be careful because in the rigid body dynamics or etc., it's necessary to work with, instead of symplectic, is Poisson, no, the Poisson system. But also, well, there are many ways, but I think that it's possible. It's necessary to, for me, it's possible to use, to consider, as in Alan Weinstein proposed, to use this framework for algebra. For me, it's simple. And then it's possible to lift all these things to these prolongations, if you want, which is a kind of tangent bundle also, but is the prolongation and the dual of the prolongation, where is the Hamiltonian mechanics. And then you are all time preserving the symplecticity of the things. But also I think that perhaps it's possible to work in the Poisson level also. But if you want for free, it's possible to use all these algebraic techniques, and you know quite well, and to produce exactly more or less the same thing, but changing the t, the tangent, by this t, calligraphic t, which is prolongation. And there you have also symplectic sections in place of symplectic force. But you are for sure recovering all these results, even for the case of reduced systems, of course, which is quite interesting, of course.
Thank you. I don't know if someone else has any question or comment. In the chat, Margarita say, thanks. Do you know if it is possible to define a metric in the tangent bundle such that the lift of the retraction is a retraction with respect to this metric?
Well, this is a very nice question. I know, Margarita. Well, it's possible to lift the metric. In some cases, you are losing this. It's a Riemannian metric. This you obtain a semi-definite metric. This is the typical, the lift, you know, the tangent lift is of this type. But I think that is not a problem for this, and unless for these numerical problems, of course. I don't know, for instance, for optimization, perhaps it's a problem to use this lift, but you are using this Riemannian metric is low, the lift is a semi-Riemannian metric. But this is something interesting to explore because, you know, you have the exponential map it's an example, and you can lift the exponential map, which is the tangent, and then the involution. And this is precisely the exponential map of this lift, which is, in this case, is semi-Riemannian. But this is an interesting point to also to study, Margarita.
Thank you, David. We don't have more time for questions. Maybe at the end of the session we can catch up all the questions. Let me share my screen now.
And you are there.
Yes, but I don't know. Can you see my slides? Can you see my slides? No.
Yeah, yeah.
Yes. Okay.
Yeah.
Let me start. I need to be stand up to be more quick with the time. Sorry. Well, I introduce myself, or not by man. Well, today I'm going to talk about how to use Gaussian processes, Bayesian statistic technique, for the learning process of a control law for multi-agent systems. Basically, this comes inspired by biological and physical mechanical swarms. So in biology, we have multiple kind of swarms, like macrobiological swarms, like penguins, fishes, bees. This is a picture of the Patagonia in Argentina, where I am from. And also we have micro formation in multi-particle swarms, like granular rods, dissipative gases, cells, etc. But the people that know who I am, that know that I'm very motivated by robotics applications instead of biology. So robotic swarms are coming to little by little. Here appears two examples of projects that are running just now. The one is from EpiFel, that is a surveillance task with quadrotors, with drones, that they inspect some area and help to the workers to stay safe, for instance, or help to assist to the worker if someone has some problem. They connect with the emergency system, and then they come for the worker, etc. And the communication is decentralized. It's only known by the nearest neighbors, the communication into this graph that appears here in the first picture. The second one, in the first one, all agents are the same, the ones that are connected in the network, but the second one is the project ASAP of Naomi Leonard in Princeton that explore how to do environmental monitoring with sampling and machine learning techniques for communicating with different vehicles. It's for pollution and climate modeling. The project, but both situations, both projects are very inspiring to me to develop machine learning tools for control theory and for robotic swarms or multi-agent systems. So anyway, robotic swarms have some limitations for the coordination of the robots. The main limitations are these ones that I list here: computational and the memory. And I will focus in the limitation of the physical modeling, where some dynamics is unknown, some dynamics of the system is not known, and we only have partial data of the system, and also the communication problem. So mainly when one works with multi-agent systems, control protocols are centralized. That means that all agents all know all the information about the other agents in the team, but to help to the communication and the computational time, decentralized approaches are more powerful, where the communication is only shared with nearest neighbors. So based on this inspiration, the problem that I will work in this talk is the modelization of dynamical systems with data-driven models. Basically, we know a lot about parametric models. We know a lot about control of parametric system based on parametric models. But for instance, when a human enters in the loop, we can produce disturbances into the system, like in the second picture that appears here, a doctor that assists some patients with a robotic manipulator that is a soft robot in this case, that also doesn't have a real physical model of the system. So this comes from inspiration. Basically, the main problem is that parametric models are time-consuming or unfeasible, and they have a limited number of parameters to be estimated. Against this problem, there appears now a lot of data-driven control approaches, like neural networks. The problem with neural networks is that you cannot give safety guarantees for the system. We cannot give convergence results for the system, for instance, to control in an asymptotic, stable sense the control system. And then there is a real technological need to build data-driven control algorithms with safety guarantees. So an overview of the modeling of systems. So we start with the system model. Then systems can be linear or non-linear. For linear systems, there is a lot of analysis, interpretability. We know a lot. There appears problems of robustness, yet they are not as easy as we can think, but we know a lot. For nonlinear models, they can be parametric or non-parametric. For parametric models, again, there is a lot of theory developed based on Lyapunov stuff, etc. But the problem is that for some kind of hard model of robots, like soft robots, parametric models are not accurate or flexible. And for that reason, people start to study data-driven models, how to model a control system or the dynamical system based on data that we know from a model a priori. So along this talk, I will try to convince you why our data-driven models are powerful, in particular for control proposals. This is the overview of my talk. I will start, since my problem is a multi-agent system problem, I will talk about the formation control problem. First of all, basically a formation control problem is that we have a team of agents, like drones. They lift off and they fly away until reach a desired shape, a desired formation, and stay there with zero velocity. They don't move, keeping the formation. That is floating control. So we will focus only to reach the formation and stay there. Yes. So this theory for formation control, the theory that I will comment today, is based on rigidity theory. To talk about rigidity graph or rigidity frameworks, we first need to introduce what is a framework. A framework is a pair, GP, where G is an undirected graph, where N denotes the set of nodes, the set of vertices. Basically, they contain the information of each individual agent, the dynamics of each individual agent, and E is the edges of the graph that describe the connection between the agents. The graph is static and time invariant, and P is a vector of positions. So this theory is for 2 and 3 dimensions. So we want to reach the desired shape. For robotics, is not needed more than 2 and 3 dimensions. So D here means 2 or 3. So associated with a rigid graph, with a framework, we have a distance function that is for each edge that is written here, where we can express this distance function as follows. Here D is a diagonal matrix, where C is the relative position between the agents. That means the difference between Pi and Pj. Yes? So C from now on will denote the relative distance between agents. So a graph is rigid if it's not possible to smoothly move one of its vertex without moving the others while we maintain the distance given by the function f, the distance function f. Here appears two examples that clearly the first one is rigid, but the second one is not rigid because we can maintain the distance moving smoothly one or two of the nodes. This theory of rigidity was developed by Asimov and Ruth. This is the first reference that I know about the framework of rigidity of graph. And associated with a rigid graph, there is a rigidity matrix that is defined in terms of the distance function, or we can define it through this diagonal matrix of relative positions, and this B means the incidence matrix of the undirected graph. The bar means that the incidence matrix is extended with a Kronecker product to fit the right dimensions of the problem. And this is very important for the stability analysis of the formation control problem, this property. So also with rigid frameworks, we have a distance error. Here D denotes the side distance between the agents. And there are two properties that I will use. I don't want to focus on this property. Basically, infinitesimally rigid frameworks and minimally rigid frameworks are properties that for me give us some information about the rank of the rigidity matrix and the quantities of agents, and that helps to develop a result or to conclude a result that is used for the stability analysis. That is that if the rigidity matrix has full rank, the rigidity matrix has full rank if the framework is minimally and infinitesimally rigid. This will be used for the stability result that I will show at the end of this talk. And also, we want that agents reach the desired shape. So the desired shape is defined in this way through the relative position between the agents and the desired distance. So what is rigidity-based formation control? So we will consider double integrator systems. That is, we want to control the acceleration of the system. P dot is the velocity, P dot equals V. V dot, the acceleration, is equals to a control law, so we want to control accelerations. And if we use this control law, where here E denotes a stack vector of relative positions between all the agents, and K is a gain matrix for the agents where the gains are all positive, then this system is stable, so we can, with this control law, we can reach a desired shape, as in exponentially stable, and it's called double integrator formation stabilization system, the closed loop system. So with this control law, we construct the closed loop system, and this is a stabilizer system. So in addition, this system can be written in this form in the last part of the slide in terms of the potential function, and artificial potential function that is an elastic potential basically between all the edges in the graph. So for me, study a formation control problem will be equivalent to study a double integrator formation stabilization system by prescribing this the control law. So to learn this will be extended with some unknown dynamics in some minutes. And to learn that unknown dynamics that we wish to learn, we will use Gaussian processes as data-driven model for the training and prediction of the system. Basically, well, I'm not a guy of statistics. I'm someone from geometry, so I will try to make my life easy and run a little bit in this part. But the Gaussian processes are a technique from Bayesian statistics that helps or allows to combine the previous knowledge with new data from the model to obtain a better model of the system by using Bayes' theorem. Basically, here M denotes the model, D the data, and theta is the previous information. Sorry. So Bayes' theorem is expressed in this way. Now, the posterior distribution is like the likelihood distribution times the priori distribution. Now, the priori distribution is the prior knowledge without data, the posteriori, the new knowledge with the updated data, and the likelihood of the data D with model, and this is the likelihood of the data D with model M and parameters data. So a Gaussian process is a collection of Gaussian distributed random variables such that any finite subset is a multivariate Gaussian distribution. Basically, a Gaussian process, f of x, is defined through the mean and the covariance, and the basics of Gaussian processes appears in the book of Rasmussen that I cite here. And the good part is what I will comment now about Gaussian processes. These Gaussian processes help us to learn the model of the system online. And I will explain what means that. Are uses for the training and prediction. Here is very technical, so I will skip this slide and will try to explain how to use Gaussian processes for training and prediction with this graph here, with this picture here. So the first picture, yes, the one here is the space of all possible a priori models, the parametric models, and then we have some data of the system. Then with that data, then we can start the process of the learning, and we don't have only a 0.1 estimation of the data. We have also a probabilistic distribution over this estimated data. The good part is that this plays the role of posterior distribution now, but the good part of Gaussian processes is that this posterior distribution is again a Gaussian process. So it doesn't stop the process there. Since this is a Gaussian process, I can obtain new data and update the model without the need of start all the process again. And we have different situations when we include more data into the stochastic process, and then we stop at some point, maybe because there is no more data, and because the battery is still good at that moment, and we finish with the posterior distribution. The advantage of this is that, as I commented before, the posterior distribution is Gaussian over space functional, and we can update the posterior distribution with the new data by using Bayes' theorem. This gives a probabilistic approach that is robust against Gaussian noise and gives an explicit description of the uncertainty of the system. The disadvantage is that it's computationally expensive, and I will run because I have 4 minutes. But basically, the problem that I want to explain quickly in a couple of minutes is how to use data-driven techniques based on Gaussian processes to learn an unknown dynamics in a formation stabilization system in order to design a decentralized control law in order that the agents reach a desired rigid formation. Here is a picture that explains more or less how is the process. Before Gaussian processes, one can start with one other approaches, now data-driven approaches in general, start with the system and some data, then we can construct the data-driven model and then make predictions on the data-driven model to design the controller. With CPs, here we have first some a priori information of the model. Maybe we know that the model is sinusoidal or is linear or is cubic, or we have some data, no? And then this a priori information together with the data helps to construct a CP model based on data-driven models. And then we can make the prediction by using this new improved CP model, not only with data and recollecting data over the time, to design a controller that exponentially reach the desired formation. So this is why the learning is online. Basically, we can collect new information, including to the system, since the training data is depending on time. So we can at different time collect data and improve the model of the system. And we want to estimate, we use the CP models to learn the unknown dynamics, basically by learning the residual, given some estimations that can be given by using techniques on system identification or set to 0 a priori at the beginning. We can use this estimation to learn the residuals and therefore learn the non-dynamics. So what is crucial also for the result that I want to give today is how to model how is the model error, no? How is the probabilistically bounded the model error. That is a result that is classical in the literature, and basically one updates the classical result in this paper of IEEE Transactions on Information Theory based on the problem that we are working. For instance, this result was developed on R. Then if you have more degrees of freedom, or if you have more dimensions in your space, it can be easily extended to arbitrary dimensions, and then we can extend this to manifold. So it's some lemma that people use it and extend depending the situation that is working. What is also crucial is a result of stability of dynamical systems, of Hamiltonian systems, done by Doppler and Francesco Bullo in this paper of 2011 in Science Journal of Applied Dynamical System, that basically give us a way to characterize the equilibria for not only one system, but for a family of systems. So if we consider a family of one parameter system with double integrator stabilization dynamics, H lambda, given in this form, then this system, yes, with this potential function B, the one that we are using for formation control, interpolates all convex combinations between a dissipative system for lambda equals 0 and a gradient system for lambda equals 1, a conservative system. So what they show is that for all lambda between 0 and 1, the equilibria set of H lambda is given by the set of critical points of this potential function B, and is independent of lambda. That's the good part of the history. And then using that for any equilibrium of H lambda for all lambda between 0 and 1, the number of stable, neutral, and unstable eigenvalues of the Jacobian associated to the Hamiltonian H lambda are the same and independent of lambda. So it doesn't matter which lambda I will use, but I will obtain the stability for the same stability for all different lambdas, as I understood this result. So one can use lambda equals 1, lambda equals 0, or lambda equals 1/2, that is the lambda that solves our problem. So using this result, one can show that these control laws that appears here in terms of the gain matrix, the rigidity matrix, the estimations, and the mean prediction of the residual with the data guarantees that the error in the conversions to a desired shape for all the agents is uniformly ultimately bounded in probability by this quantity here, where omega is a compact set that appears in the previous lemma I showed here, and this EEB is the stack error of relative positions, errors and velocities for deformation stabilization. This control law is a vector node for each agent, and the individuals one only depends on the distance between nearest neighbors and the data in which is based each agent. Each agent learns its own dynamics only based on the interaction between the distance between nearest neighbors and its own data. This is because it's decentralized. And we apply this to a particular control problem to learn some vector fields that act as disturbance in our system, and also this technique of how to learn dynamics using Gaussian processes, how to design a control law based on data using Gaussian processes was used. I will skip the sketch of the proof. Was used to model unknown dynamics for aerial vehicles. Basically, all the stuff that we use Lyapunov functions. So it's Lyapunov techniques, basically. And what we did was start to extend this direction to aerial vehicles. And because data-driven control laws doesn't exist for cooperative, complex, and multi-agent systems with safety guarantees, the probabilistic bound that we have here is what guarantees safety results in the program. So let me finish with why I comment here this in this session is because there are some results in the literature that my controller is at the end an adaptive controller. So we collect data and we improve the controller thinking on adaptative nonlinear control. So there are some new papers in the area that use contraction metrics to solve the stability of some mechanical system, for instance, like Lagrangian system. And I guess that contraction metrics can be a tool to study exponential stability in a more mathematical way, not only using Lyapunov stuff in a more accurate way for this kind of problem. For instance, for flocking behavior or the void of birds. No, if we want to study the limit of the trajectory, so how to reach in the long time. And this is all. Sorry to run. If there is no more time. Sorry, I have a video also, but can I show a video?
I think it's better we start the second talk, the third talk, and if we have time at the end, we go back.
Okay, if there is time to understand better my talk, I have a video of the presentation. Easily is a 1-minute video, so I would be very happy if you can give me some time at the end to show how to employ this result in a particular program. Okay, thank you very much. Sorry for going very quick, but the time is too short. I'm happy to answer any questions.
Thank you very much. So I guess we don't have enough time for Q&A right now, but maybe at the end of the session. Please, the next speaker gets ready.
Okay. Can you see and hear me?
Yeah, perfect.
Perfect.
Yes.
And okay, so I just start, yeah? Okay.
Yes.
So my name is Jacob Goodman. Thank you to the organizers for having me today. And today I want to talk about an attitude and position tracking of 2 quadrotors carrying a rigid rod with elastic cables. So sort of an application of some of the Lyapunov analysis. And this is a joint work with my PhD supervisor, Leonardo Colombo, who just gave the talk. So the basic problem at hand is we have 2 quadrotor UAVs, which are just drones with 4 propellers. And they are transporting a rigid rod load via 2 elastic but inflexible cables. And the idea is that we want to track a trajectory, arbitrary smooth trajectory for the center of mass position, as well as the attitude of this load. So for this problem, our configuration space will be as follows. This first component here will be describing the position and attitude of the rod, particularly the center of mass position of the rod. The second component here, or the second and third components, will be describing the attitudes and lengths of the cables. And the final 2 components here are describing the attitudes of the quadrotors. And just observe that we don't need to include the position of the quadrotors in our configuration space. They'll already be uniquely defined in terms of the other variables. So the first step in any problem like this is to first find the dynamics of our system. And we do this using a Lagrangian formalism. So as usual, we'll construct our Lagrangian as the kinetic energy minus the potential energy. And I'm not going to go into much detail about how we found these or the exact steps in deriving the dynamics, but in the end, we're using the Lagrange-D'Alembert principle here. And in our case, for these virtual works, these are representing some non-conservative external forces in the form of two controllers. The first being our total thrust controller, which really is a scalar quantity, but we write this in vector form, this uj, which we think of as just a vector pointing vertically upwards from the quadrotor in the body frame, and then translating this to the inertial frame via our matrix rj. The second controller here, or the second and third, there's two for each j here, j equals 1 and 2. Our other controllers are these total moment controllers, and these are in essence describing the proportions between the thrusts of each individual propeller on the quadrotors. And this is what allows us to control the attitude or the roll, pitch, and yaw of the quadrotors. And the final non-conservative force is a spring damping force, which is really just something from physical considerations. We don't want the elastic cables to oscillate indefinitely, and we wouldn't expect that in practice. So if you were to expand out the Lagrange-D'Alembert principle after choosing some appropriate variations and conducting the variational analysis, you get the following dynamical system. In particular, these first two equations here are describing the translational and attitude dynamics for the rod. Equations 3 and 4 are describing the stretching and attitude dynamics for the cables. And the 5th and 6th are the kinematics and dynamics for the quadrotor attitudes. And again, in any case where there's J, this runs through J equals 1 and 2, describing each of the quadrotors or cables. And here we've introduced some auxiliary variables, as well as the effective mass and moment of inertia. It may not be very clear looking at this, but there is a problem introduced from the fact that we have this variable cable length. There are some other groups that work on similar modelizations, I would say. None of them have really worked with the rigid rod, but some of them with transporting rigid bodies via quadrotors. For instance, Taijun Li's group in the Flight Dynamics and Control Lab at the George Washington University, as well as Kushal Srinath at UC Berkeley. And in both cases, they work with inelastic cables. And the convenience there is that the resulting system is differentially flat. And that lends itself to a control scheme. In essence, we couldn't use that control scheme here because of this variable cable length. So the first thing we'll do here is to take advantage of the fact that in applications, elastic cables are often very stiff and have high damping. This corresponds to the spring constant K and the damping coefficient C being quite large. So in particular, we can think of these as being modeled by some other constants divided by some small parameter epsilon or epsilon squared here. We'll further make a change to variables so that we have our cable length represented as the rest length plus some small perturbation, as well as the stretching velocity as just being a small perturbation around 0. So what we can do here is substitute these back into our previous dynamical system and compress it into this form, which is known as a singular perturbation model. 7 here describes the slow dynamics, and 8 represents the fast dynamics. And the strategy from here is to evaluate the system at epsilon equals 0, which would then correspond to an infinitely large spring constant and damping coefficient, which one would hope would yield inelastic cables. And from there, you have an algebraic equation in terms of G, which, assuming sufficient regularity, you could solve via the implicit function theorem for Z in terms of T and X. In our particular problem, this can be done very explicitly. So we do obtain some function H, and we substitute that back in for Z in the slow dynamics, and we obtain the reduced model. This is the reduced model down here, and it can be seen that this is the exact model one would obtain if they began with the same problem, but with inelastic cables and ran through the same variational analysis. And a good reference on this stuff is Khalil's book, Nonlinear Science, or Nonlinear Systems. And in particular, it helps to justify the inverse problem. So there's a few results in this book that tell us that basically we can design a control scheme in this reduced model. And if this control scheme yields exponential tracking, then we can lift the controllers here back to a controller or control scheme for the original elastic system. And we won't get exponential tracking, but rather will remain within some epsilon ball of the trajectories of this reduced model, where epsilon is the parameter we chose from before describing how elastic or inelastic our system is. So the strategy now is just to work within that reduced model and design a control scheme. In particular, the way that we design these controls is to break our controllers into components which are parallel and perpendicular to the cable attitudes. So such a decomposition can be written explicitly as follows. And the main motivation for this is if you really study the dynamics of the reduced model, you can see that only the parallel components influence the rod dynamics, while only the perpendicular components influence the cable dynamics. And in that sense, you can think of these components as being individual and in some sense gain an extra controller. So before we design the full control scheme here, we're just going to apply this quasi-feedback linearization. So this is not technically a feedback linearization because the resulting system is not linear, but it's along the same vein where we're taking our controllers and defining some new controllers to be designed later, of course satisfying the constraints on being parallel or perpendicular as needed. And then we're going to subtract out some of the nonlinear components as necessary. And applying this, we obtain the following system, which I think looks much more tractable. And something important to notice here is that these equations 23 and 24, denoting the quadrator attitude dynamics and kinematics, are decoupled from the rest of the system. And as is the controller, the moment controller MJ doesn't appear in any of the other remaining parts of the system. And as such, we can design these control schemes independently. And there are already some references that have taken care of that problem for us. For example, this paper by Taijun Li here. There's a controller designed here that yields near global exponential tracking. So in particular, we can ignore these attitude dynamics and just focus on the remaining parts of the system. So in order to finish our control design, what we need is to define some tracking errors, which is a way for us to quantify the distance between our actual trajectories and the desired trajectories. And here we denote the desired trajectories universally with the variable we're trying to track with a tilde. So we define them as follows. We're also going to define a configuration error, just some function on the Unisphere S2 for the cable latitudes. And these have the property that if all of these tracking errors and the configuration error vanish, then all desired trajectories have been tracked. So now the idea is fairly straightforward. We want to derive the aerodynamics, and then we'll design the controllers so that the origin is an exponentially stable equilibrium point in the aerodynamics. In particular, we can calculate these aerodynamics explicitly as follows. And what we're going to do is design our controllers using PD or proportional derivative controllers with some additional feedback terms. And that just means for some gains here, we're going to choose our controllers as follows. And here we've put these tildes on the controllers because these are what we want. We want these PD controllers, but it turns out that we can't use them as is because they do not satisfy the constraints that they are parallel to the cable attitudes. So in particular, we'll just choose our controllers to be the projections of these desired controllers onto the cable attitudes. And from there, it turns out that doing that yields some problems in the stability analysis, but we can remedy that by forcing our desired cable attitude to follow this trajectory here, namely because it has the property that as the cable attitudes approach the desired cable attitudes, so too do our controllers approach the desired PD controllers. And if you follow along with this analysis, you then get the following aerodynamics. And now we're just going to work on Lyapunov analysis for our stability analysis. So in particular, we're choosing our Lyapunov candidate V as follows, and we're defining it on some arbitrary bounded neighborhood of the origin. So as is when you're trying to find exponential stability, your first step is to show that the Lyapunov function is bounded above and below by some positive definite quadratic forms. In particular, this is very straightforward in our case. You can find these matrices P underbar and P bar fairly easy, and they're positive definite so long as these Lyapunov constants are sufficiently small. The next step, of course, is to show that the derivative is bounded above by a negative definite quadratic form. And this is a little more complicated. We were able to find a matrix W. It's not actually a symmetric matrix, but we can still get all the results we need by showing that the symmetric part of W is positive definite here. So we were able to obtain the following theorem, just saying that there exists some choice of gains such that that holds. And in particular, that means that for these choice of gains, the origin of the aerodynamics is exponentially stable, and thus we have exponential tracking. I'm not going to go into all the details of the proof. I'll explain a few details on the next slide, but if you're interested in reading about them in more detail, you can read the archive preprint of our paper here. So in particular, that matrix W that we found has the following form. This is an 8x8 matrix, really a 4x4 block matrix where each of these submatrices are 2x2. And what we do is make use of something called Schur complements, which is sort of a way to decompose a positive definite block matrix into conditions on the blocks. So what we have is that W is positive definite if and only if these 3, or rather 6 conditions hold, because these need to hold for j equals 1 and 2. The strategy is straightforward from here. We're going to first show that this first condition holds by just showing that the smallest eigenvalue of W is greater than 0. And from there, you work towards the second conditions. And in particular, what you need to show is that these minimum eigenvalues of WQR can be made arbitrarily large and independently of these matrices WQJ and WQRQJ. And in that sense, you can guarantee this holds. And you follow a similar strategy for 3, just yet another level of convolutedness and tedious calculations. But in the end, the strategy is fruitful because it provides, in some sense, a strategy for finding the gains necessary to make W positive definite. And we take advantage of this in the following application, or rather a simulation. So in this case, we're taking our desired trajectory for the load to be this Lissajous curve, or tracking something like an infinity symbol. And this in the plot is denoted by the red curve here. And we're also taking our load attitude to just be a constant vector. And using that strategy from before, we were able to obtain the following set of gains. And these are the simulation results integrated numerically with Euler method in Python. So in particular, this blue curve down here is the actual trajectory for our load. The green and the yellow are the trajectories for the quadrotors, which weren't something we were too concerned about, but they also track fairly well. And if we look at the plots of the errors, we see that for the load position and attitude, we have very quick convergence to 0, both for the position in, I believe, blue and the velocity in red. And we also have similar convergence to 0 for the cable attitudes, maybe with some small oscillations around 0. And similarly for the controller magnitude, we have a rather quick spike, but then we settle to a steady state solution. And this is, indicative of the fact that maybe we chose our gains too large here. The conditions we found using the Schur complements was really just a sufficient condition. So it could be that there exist smaller gains that still make this work, and you can avoid having such dramatic behavior at the onset. And the final step here is to then check the robustness of our control scheme. So we have exponential stability already, or exponential tracking. And in particular, exponential stability is robust to small disturbances. But maybe in some applications, you have wind or some other sort of unstructured disturbances that are larger than you can guarantee will work. So just to see how this works, we'll take the dynamical system from before, again, omitting the attitude dynamics for the quadrotors, and introduce these red terms here, just some unstructured but bounded disturbances. And we assume that we know what these bounds are ahead of time. And then we'll run through the same things before, using the same controls and the same Lyapunov function. We'll find that the bounding the Lyapunov function itself is quite easy. It doesn't work any differently, but the derivative obtains this extra term here, where this E matrix is a constant vector. And in particular, it's written in terms of the upper bounds on the disturbances, magnitudes, as well as some other parameters from our problem. And we can apply Young's inequality and some other facts about positive definite matrices to show that for any epsilon greater than 0, we have this following inequality. And in particular, something that we gained from the theorem that we proved earlier was that the symmetric part of W can have arbitrarily large minimum eigenvalues by choosing the gains sufficiently large, essentially. In particular, this means that we can take these sufficiently large so that everything we need is satisfied, and we have this term here as negative definite. And this leads to the following theorem. We can't guarantee exponential stability in this case because we have this constant error term here. But at the very least, we can guarantee uniform ultimate boundedness for some choice of gains. And in particular, if we take these gains sufficiently large or just choose them appropriately in general, we can guarantee that this ultimate bound can be arbitrarily small. So we can converge to an arbitrarily small neighborhood around the origin. So with that in mind, what we've shown is that in the reduced or inelastic model, we can achieve near global exponential tracking of arbitrarily smooth trajectories, and that they're robust disturbances. And the next steps here that we also did in the paper would be to then include the quadrant or attitude dynamics back into the problem, and then to translate these results back into the original elastic model via some of those results I talked about from Khalil's book. And some future work we'd like to work on is the design of optimal trajectories to track, maybe in terms of something akin to Riemannian cubic polynomials, then to construct geometric integrators for more accurate simulations and long-term behavior, and then finally to conduct actual experimental results. And that's it. Thank you for your attention. And if we have time, I'm happy to take any questions.
Thank you, Jakob.
Sure.
Since there is no question at the moment, so well, thank you, and let's get ready for our next speaker, Antonio Bloch.
Okay, so let me. So can everyone see my screen? Is that we good?
Yes.
Okay, and so I have about 30, 35 minutes maybe, is that about right?
Yes.
Yeah, so and I'll try and leave room for Leo to show his video for sure. So, and you know, feel free to stop and give me a reminder if I go up, but I'll try and keep an eye on the time. Yeah, so thanks Leo and David and everybody for inviting me. It's nice to be here, at least virtually, to see you all. So what I want to talk about today is the geometry and dynamics of circulant systems. So these are systems that mainly arise in biology. So they're related a little bit to the graph theoretic idea that you saw Leo describe, for example. So in biology, one's often interested in complicated systems with many different agents, if you like. So in many cases, you're looking at cells. And part of this inspiration for this work was really the control of cell dynamics. So this is related to some work that I've done with Indika Rajapaksa has a lab here. And there it's a control system where you have a bunch of cells and you want to control them by some agent, which is usually a protein and more specifically a transcription factor. And one's interested both in the dynamics and the control of these systems. And another aspect of this is the existence of periodic orbits. So very often, of course, in a cellular system, you want periodic behavior. You have circadian rhythms. Your body works on a kind of cycle that's 25 hours long, basically. And in addition, your heart beats and so on. So circular orbits, at least periodic orbits, are a key part of biological systems. And these tend to arise in certain kinds of graphs, and particularly so-called circulant systems, which I'll show you. So the main two systems I want to look at are so-called Sprott system, which is a sort of mathematical representation of a system of cells on a circle, if you like. So you can think of n agents, if you like, on a circle, coupled in some way, and I would like to know if the system oscillates or not. And similarly, there is the repressolator, which is an iconic example of a biological system, and in particular, an artificial biological system. So it was really part of the renaissance of synthetic biology, where people wanted to see if they could construct out of cells oscillating systems. So those are the two examples, and it turns out into this case, into a theory of the existence of periodic orbits that is described by what are called continuation methods. These continuation methods rely on Poincare maps and other sort of familiar objects from dynamical systems that I'll show you. So here is the repressolator. So in a sense, it's very simple dynamics. And the only interesting dynamics is in the way they're connected, which is, so it's a little similar to what you saw in Leo's talk, where you had a double integrator with an interesting connection. So this is what you're really seeing here. And there is a second order version of this. This is a first order version. So the first order dynamics, if you like, is just x dot equals minus x, simple dissipation. And then you have this connection, and this is repression. So you can think of each cell as repressing the dynamics of the other cell. So you can see here, for example, if y is large, then the dynamics of x is repressed. And also it's got a cyclic symmetry or a circulant symmetry, in the sense that I can get all the second equation from the first simply by shifting x to y, y to z, and z to x. And you can show that the system exhibits remarkable stable periodic orbits. And it got its fame, as I said, as being an example of something you could actually construct in a biological context in the realm of synthetic biology. So one of the things we were interested in is, is the system special or not? Are there other systems that look like it? So here is another system which you can see in a sense is more complicated, in a sense is less complicated. So it doesn't have the sort of rational repressor term, but it has a little more complexity in the internal dynamics. So again, there's a dissipative term now with a bifurcation parameter, which will be important for us. And one can also put one into the repressor-lated system as well, but then there's polynomial dynamics for the system itself. So it's x dot equals y squared minus z, and it still has the same discrete symmetry. So x goes to y to z into x and so on. And this is again reminiscent of these other synthetic biological systems. So those are the two examples. And the repressor-lated is an example of what's called a monotone cyclic feedback system. So this has become quite famous in biology. And that's where the derivative of the, if you like, the repressor term is always of a constant sign. So these systems have been analyzed by many people. There was a famous paper by Mallet, Perret, and Smith in 1990, which looked at them. The interesting thing about the Sprott system, though, is it's not monotone, and that's because you get these interesting different signs. You had x dot equals y squared minus z and so on. So the techniques that can be used to describe monotone cyclic feedback systems do not apply to the Sprott system. But nonetheless, we were able to look at techniques which describe both the Sprott system and the repressor-later model. And the main thing here, as I said, there are all sorts of background problems that we're interested in, but the main problem I want to concentrate on here is the existence of periodic orbits. And as you know, existence of periodic orbits is very hard in dimension greater than 2. In dimension 2, you have the Poincare-Bendixson theorem, which I'll remind you about, for example. But once you go to higher dimensions, it's really a difficult problem, and that's both in the Hamiltonian setting and the non-Hamiltonian setting. And one of the interesting things here is that the systems that we're looking at are Hamiltonian. So if you look at them, at least are not Hamiltonian, if you look at them, they're sort of reminiscent of sort of Lie-Poisson systems. You might think they're Hamiltonian, but they're not, and that's another important thing. And the basic work that we use to show the existence of periodic orbits here goes back to some work of Sotomayor in 1973, who showed the existence of what's called a residual set of systems with orbits having one of 3 normal forms. And that's sort of the basis, in some sense, of our work, which I'll show you as we go along. And as I mentioned, this is inspired by a whole lot of different work, mainly in mathematical biology, but it basically applies to a lot of systems with different interacting agents, and which can be described by a graph or a hypergraph. So there's related work with this lab of Rajapaksa that I mentioned earlier with Roger Brockett and Amit Surana. We've looked at control of biological systems in various senses, including the control of stem cell dynamics, the control of various networks, and tensor control systems. And as I said, in the lab of Rajapaksa, we use these so-called transcription factors, which can be used to change a cell type, basically. So there, in a sense, the control problem is the type of the cell. And a transcription factor is basically a complicated protein. And there's this famous work of Yamanaka, which won him the Nobel Prize in 2012, where he showed basically using 4 types of transcription factor, you can return any cell basically to a stem cell, to a cell associated with no particular function, if you like a liver cell or a heart cell and so on. And part of the problem there was the reduction. So if you're looking at one of these biological systems, typically they're huge, right? So in the end, if you like, you can think of millions of particles involved. If, for example, a DNA molecule has something like 3 million different sort of atoms associated with it. And you can, and so the whole problem here is to reduce it in some way. And there are various ways of doing it, which I mentioned a little bit here. And part of the problem is trying to understand these really large dimensional systems by modeling with lower dimensional ones, like the ones I'm talking about here. And part of the work in the lab is to try and capture both the gene dynamics through the gene expression and through the geometry, which is called high C. And I'm not going to talk much about that here. So the theoretical part of this is to study periodic orbits of ordinary differential equations, and the ones, of course, I have in mind are the ones I showed you. So I have an ordinary differential equation with a parameter. So x dot equals f of x mu. X is in some smooth manifold Q, mu is a parameter in R. And the main idea here is to find an example of what's called global continuation of periodic orbits for the system. And the whole point here is to find periodic orbits which are robust in the sense that as mu is varied, you still get periodic behavior. So one of the things in bifurcation theory is it's relatively easy to show local existence of periodic orbits, for example, via the Hopf bifurcation, but to find global periodic orbit behavior is actually much tougher. And of course, that's what one wants, because one wants a certain amount of robustness. So is there a range of mu where you get periodic behaviors? And this is what we are able to do based on the so-called global continuation theory and the existence of a so-called one form, which I'll talk to you about. And there is a bunch of work that sort of precedes this by Fuller, Alexander and York, Mallet-Perret and York, and so on. And that's sort of related, but didn't exactly fit what we wanted to do. So that's where we came up with this form idea that was useful. So one of the difficulties, in fact, in proving these continuation results is that one, in the literature that I just mentioned, you need a sort of previous existence of upper bounds on the periods of the periodic orbits, or sometimes what are called virtual periods, which means basically recurrence after sort of end trajectories through the transverse surface describing the Poincare map. And that's something that you can't really find exactly. So our main contribution here in a way was doing away with that requirement, and that required coming out with a certain one form that I'll talk to you about. And it's related, in fact, to the Lyapunov theory, for example, which you saw in Jacob's talk. So here's a little background. So we were looking at equilibria in periodic orbits and the associated tools of analysis, Poincare maps and Floquet multipliers. So I'll show you a figure about this in a moment, but the idea is if you have an equilibrium f of x 0 equals 0, we say that the system is in equilibrium. So x dot equals f of x 0 is equal to 0. So in general, if I have a normal system, you can look at the eigenvalues of the Jacobian. This gives stability information. So if all the eigenvalues have negative real part, then you get exponential decay, as we saw in the previous talk. What we're interested in here is periodic orbits rather than equilibria. So let's suppose that we have a solution gamma of t satisfying gamma of large T equals gamma of 0 for t, for big T in R. We say that's a periodic orbit. And if t is equal to the inf of t, such that gamma of t is equal to 0, we say that t is the least period of gamma. And if t is greater than 0, we say that gamma is non-stationary. So of course, if t is equal to 0, you're back to the equilibrium. And the basic tool sort of for both for visualizing and analyzing it is to consider a hypersurface intersecting gamma and look at what's called a Poincare map. So here's a picture. So I have some sort of periodic orbit. I put a hypersurface, which is transverse to the orbit. And I look at the repetition of the orbit as it hits the surface. And then I do something I do similarly to the equilibrium case. I look at the stability of the map, which takes me from one intersection of the surface to another. So the Floquet multipliers are the eigenvalues of d gamma 0 p, the map which takes the tangent space of S, t gamma 0 s to t gamma 0 s. And again, the multipliers in this case give us stability information. So in this case, if they're all inside the open unit disk, then all initial trajectories near gamma approach gamma exponentially fast. So that's the analog of exponential stability for the equilibrium case. And of course, you run into difficulties when you're on the disk and things are more complicated. And so the famous theorem in this case in 2 dimensions is the Poincare-Bendixson theorem, which says that if R is a closed bounded set of the plane, x dot equals f of x is a differential vector field on an open set containing R, and R does not contain any fixed points, then there exists a trajectory that's confined in R in the sense that it stays, in R and stays in R for all future time. And then you can show that either C is a closed orbit or it spirals towards a closed orbit. So in either case, R contains a closed orbit. And so the basic idea is you either have fixed points or closed orbits. So things are really kind of nice in 2 dimensions in the sense that if you have a nice system like this and you don't have an equilibrium, then you have a closed orbit. But this fails in higher dimensions. But there are cases, in fact, which are sort of similar, and that in higher dimensions, and those are the monotone dynamical systems that I mentioned earlier, which behave a little bit like the Poincare-Bendixson setting. But that's not true in general for the systems I'm looking at here. So anyway, so if you don't have the 2-dimensional case, how do you prove the existence of periodic orbits? So one thing is the Hopf bifurcation theorem. So suppose I have a reasonably differentiable 1-parameter family, again, x dot equals f mu. And let's suppose that x0 is an f mu to the -1 of 0, such that, again, the Jacobian has a pair of purely imaginary eigenvalues. Then you can show, and I won't go through all these conditions here in instance of time, but there are just a few sort of reasonable local conditions that tell you if you have this pair of purely imaginary eigenvalues and you change the parameter in a reasonable way, then you end up with a periodic orbit. And that's the Hopf bifurcation theorem. So, so this is one of the conditions that one needs. So it's a sort of very precise condition that you can write down depending on the differential equation that you've got. And there are 2 different cases that you can get. There's the subcritical Hopf bifurcation and the supercritical Hopf bifurcation. And you can easily look to sort of decide whether you get it or not by looking at the Floquet multipliers inside and outside the unit disk. And that tells you whether the so-called, whether this periodic orbit is hyperbolic or not, basically. And the nice thing about the Hopf bifurcation theorem is it's a qualitative theorem, and it's easy numerically to verify the hypotheses. So as you can see, it's a little complicated even in general to do it explicitly, analytically, but at least qualitatively, numerically, you can do it. And the only real problem for that is it's only for a small value of mu, so it's very local. So for example, you know, if at mu, you end up with periodic orbits, you don't really know how much you can change mu and still remain with periodic orbits. And that's the condition that we want to look at here. So if there's this bifurcation at mu0, you don't even know, for example, if you add an extremely tiny little perturbation to mu, whether you still get periodic behavior. So that's the thing that we basically want to sort of handle in this setting. So there are other techniques as well, as I mentioned earlier, for looking at periodic orbits. And so there are interesting systems where you can think of, even though the system is n-dimensional, you can project it to a 2-dimensional system and then still get a sort of version of the Poincare-Bendixson theorem. And this, for example, can be found in this work of Malek, Array, and Smith that I mentioned earlier, and applies to these so-called monotone cyclic feedback systems, which are an important class and very important for biology. And another important case is the Hamiltonian case. So proving the existence of periodic orbits is also very interesting. There's this famous Arnold conjecture, and this was analyzed by Rabinowitz, Weinstein, Zender, and so on. So there are conditions when you have a Hamiltonian structure, you have a Hamiltonian, you have a symplectic structure. Again, there are nice conditions you can use to prove the existence of periodic orbits, but again, it's not trivial. But again, in this particular setting, we don't have that. And there's also the so-called torus principle, which is based on Brouwer's fixed point theorem, and that actually is more closely related to what we're doing here. And we do use this work of Brockett and Burns, which Chris Burns wrote about shortly before he passed away, sadly, a few years ago. That's actually relevant to what we're looking at. So I'm going to start. So I'll try and say a little bit about the general theory, just depending on time, but I'll mainly talk about how we can, illustrate the general theory for the Sprott system. So here, anyway, so let me just start off with some pictures. So here's the Sprott system. So you remember that's this polynomial system with dissipation. Here are a couple of MATLAB simulations. So this is one without damping. And so remember there's X, Y, and Z, and you can see you get this very nice periodic behavior with or without damping. So this is the undamped case. You get these rather beautiful oscillations. If you add a little damping, it becomes even more regular. So, and you can see it's extremely robust. So you can just plug the system in with virtually any value of the damping and you get beautiful behavior. And the same is true of the repressor later. So that's the nice thing about it. And the orbits have a rather beautiful complexity. So if one does a better simulation, so these are Matt Qualheim simulations using Python rather than MATLAB. So here are some trajectories of the Sprott system. So here are some trajectory segments of 150 time units for mu equals 0. So each of the top 3 figures consists of a single trajectory segment with a different initial condition. So you can see it has this rather beautiful behavior. And these 3 trajectories are superimposed in the bottom left figure. So you can see that you get something that looks a little bit like a torus. And then finally, the bottom right figure, again, a single trajectory condition, a single trajectory with another initial condition. And the nice thing is you can see it certainly looks like it's periodic, but it's actually quite complicated. And in fact, with various values of the parameter, so we call it the Sprott system. I mean, we sort of came up with it independently, but it turns out that there's a physicist at Wisconsin called Sprott who also looked at systems like this just numerically. And he claimed to see for some values of the parameter that in fact you get chaos as opposed to periodic orbits, although we haven't seen that. So it may or may not be chaotic in various reasons, but certainly in other reasons you can get periodic behavior. So here again are some other versions of the dynamics. So here's a trajectory segment for mu equals 0, and there's a sphere there that you'll see that plays an important role, and also some internal dynamics. Here's another trajectory for a little bit of damping, and another trajectory with even more damping. So that's the kind of dynamics that you get. And it's somehow, as you can see, it's all related to the geometry of R3 in which it's embedded. And there's this a sphere that plays a role, and I'll try and explain that. So the first thing is that you can find a compact set containing all compact invariant sets, which is as follows. So you try and write down this sort of kind of pseudo-Lyapunov type object. So I define the function R3 to R via v of x, y, z equals x plus y plus z. I compute the lead derivative of v, so the derivative along the flow. And for any level set, for any c greater than 0, the sublevel set, v dot to the -1, is the closed ball of radius through root 3 into mu plus 1 squared plus 4c over 2, centered at 1 plus mu over 2 times 1. So that's that ball. That's what we're looking at. And in particular, you can see that the 0 sublevel set of v dot is at the midpoint of 2 equilibria on the diagonal. So there are 2 equilibria being on the diagonal x equals y equals z, and these are the antipodal points of the bounding sphere. And there are 2 planes, v to the -1 of 0 at the origin and at the other end of the sphere, which are tangent to the sphere at the antipodal points. So that's sort of the geometry. So the planes and the sphere sort of describe the geometry in a nice way. And you can see that the subsets v to the -1 of -infinity 0, at one end, and v to the -1 of +infinity, of 3 plus 1 q to +infinity, are positively and negatively invariant, respectively. And so trajectories in these regions tend to infinity, but we're sort of interested in the local dynamics, which could be periodic. And you can check that any compact invariant set then must be contained inside, the region v to the -1 of 0 into 3 plus 1 over mu. And we want to refine that a little further to produce a compact set containing all compact invariant sets. So that's what you can do. And so it's just basically a computation, but you can check that every compact invariant set is defined in this object here that I've called K mu. And you can try and describe it a little bit so that there's a picture. It's a little more complicated than what I've shown, but basically it's sort of related to these tangent objects and the sphere that I described you earlier. But basically that's just a depiction of this compact invariant set. And so we just like to unwrap that a little bit to describe the dynamics. So the idea is, one way to do it, and there are a lot of ways to view this actually, one way to do it is to write cylindrical coordinates for the rotation of the flow. And why you might think of doing that is because, you saw the sphere and there's this line, x equals y equals z. So, and if you looked at some of those pictures, you saw dynamics more or less along that, sort of twisting along that line. So if you want, one way to think about it is to write down cylindrical dynamics with the cylinder about the line x equals y equals z. And so that's what we do here. So you can write down an orthogonal matrix n, which gives you a transformation to these dynamics. So the w-axis corresponds to delta, the original coordinates, that line, and the u and v axes determine an orthonormal coordinate system perpendicular to that. And so you can define, with that in mind, cylindrical coordinates rho, theta, and w, and obtain equations of motion, these new coordinates that I've written down here. And you can show that there exists an epsilon greater than 0, that for all mu between -1 and 1, theta dot is less than minus epsilon whenever x, y, and z are at k mu modulo delta. So you're in that compact invariant set and just outside delta. So that's sort of a bound on the rotation of theta, which is already a good sort of start for the periodic behavior. And then in addition, you can show that for mu -1 between -1 and 1, all equilibria lie on the diagonal, and all periodic orbits are contained in k mu with a sort of a winding number less than or equal to -1. So that's already kind of nice dynamics. And in addition, you can show, the delta is invariant. The dynamics restricted to delta is actually given by this very nice simple system here. And you can show that, that the vector field has at least two equilibria, 0 and 1 plus mu times 1. For mu between -1 and 1, they're only the equilibria. And then, in addition, you can show that you get a subcritical Hopf bifurcation at mu equals -0.5 and a supercritical Hopf bifurcation at -0.25. And so the first one produces an exponentially stable limit cycle, and the second one produces an exponentially unstable limit cycle. So these are already two kind of nice results, but it's sort of local. So what you've shown basically is that there are Hopf bifurcations at these two equilibrium points, and you get either stable or unstable periodic orbits. And that's already nice, but it's, as I said, it doesn't tell you anything about the global stability, and that's really was sort of the main sort of focus of our work, although this is already kind of interesting. And you can do a similar kind of analysis for the repressor later as well. So now I'd like to say a little bit more just about the general theory of how you generalize this to global bifurcations, if you like. So in the remaining time, which I guess is about 10, 15 minutes, I will say something about that. So there's this beautiful theory of global continuation of periodic orbits that goes back to Aligood in York and even further back to Sotomayor. So again, let's consider a general system, x dot equals f of x mu with a parameter. And we want to consider, exactly as I said, the idea of continuing periodic orbits in some global sense, which means instead of just having the Hopf bifurcation I showed you earlier, can I change mu? Can I still show that I have periodic behavior? So the first thing is a definition of what's called eta L global continuity. So for each mu, so for the bifurcation parameter, let's take an inclusion, I mu, which takes q into q cross r. So I mu is just x mu. And then the definition of eta L global continuity is as follows. So for L greater than 0, eta a closed form on q cross r, and a connected component of the non-stationary periodic orbits of the equation 0.10 here. So basically, you'd like a set of periodic orbits, like a kind of dense set. And then let AL be the subset of points on periodic orbits where this integral is fixed to some number L, and A less than or equal to L, a subset where it's less than or equal to L. And let's consider gamma, let gamma be a periodic orbit with an image gamma inside the set. So I've got the set where I have a bunch of periodic orbits. I look at the connected components, and then we say that gamma is E to L globally continuable if at least one of the following holds. So A modulo gamma is connected, or you basically have two connected components with a couple of other technical conditions. So basically the idea is you just like this set AL to be a nice sort of fat set in some sense. So you've got a nice continued set of periodic orbits such that when you change mu, you still get periodic behavior. And so the main results really are about existence of that. So the key results, which I'll just describe briefly here. So you have global continuability for these non-generic families. So if F is a family of vector fields and eta is a closed form, if A is a component of non-stationary periodic orbits and gamma is a periodic orbit with an image gamma less than A, as long as gamma does not have a flock A multiplier, and if you define L with L greater than 0, you can show, in fact, that you do get this global continuability, which is it's sort of a technical thing, but it leads to the main results. So the first thing is you can show that basically under these hypotheses, you can, in fact, get global existence of periodic orbits. So as long as you can find such a form that I just described, under certain technical conditions that I won't worry about here, but basically what it says that if you think again Hopf bifurcation, instead of just having a local Hopf bifurcation, you can show that as long as mu is greater than or equal to mu0, and the previous theorem 5 is satisfied, you get this sort of large set of periodic orbits. And in particular, you can get global existence of periodic orbits following a Hopf bifurcation. So again, it's kind of restricted. There are a bunch of technical conditions sort of related to the to the flock A multipliers and how they intersect the orbit and so on. But basically, they do. It looks kind of restrictive, but it's not too bad, and it certainly fits both the examples that I described here. So it applies both to the repressolator and the Sprott system. That's the key thing. And so instead of just going through the details of the theorem, let me just describe a little bit about what this means. So what is the continuation idea? What are we really doing here? So basically, the repressolator and the Sprott system undergo Hopf bifurcations. So we know the periodic orbits exist for some parameter values, maybe just one parameter value. But the question is, how small is epsilon? And can we solve how small is epsilon? So if you change it away from mu, how much do you get? That's the basic idea. And the idea is sort of basically, it uses degree theory. So the degree theoretic result is sort of the following. So let's suppose D is an Rn, a compact domain. I have a smooth one parameter family of maps such that G mu 0 has finitely many zeros. The derivative is invertible, and G restricted to the boundary has no zeros. If you look at the Poincare Hopf index, which is basically the number of plus eigenvalues, the signs of the determinant of D, then if mu greater than 0, if mu1 is greater than mu0, such that G mu has no zeros in a certain interval, there exists a 0 of D mu for all mu in mu0, mu1. So that is a sort of degree theoretic result for a function. You just want to know if you have a function depending on a parameter, it has a 0, you change it a little bit, does it still have a 0? And basically you want to do the same thing for the sort of functions describing a periodic orbit. So that's sort of the idea of continuation, and it rests basically on this degree theory. So this is a continuation result for an index of the index of the function, and there are other continuation principles. There's the Lefschetz and the Connolly index, which apply to various ODEs. They're famous results in that regard. And the question is there an analogous index for these periodic orbits that we're looking at? So that's really the idea. And in fact, there exists multiple indices for periodic orbits satisfying continuation principles. And so the work of York and Alexander and so on sort of came up with such an idea. The only problem is it was very hard to just verify the conditions. And in fact, you couldn't verify the conditions for the systems that we were looking at. And the sort of index thing that we came up with for the for this one form that we mentioned, this continuation one form, kind of solves that. So that was the point of the work that we did. And let me just, so I guess I have about 5 minutes. So let me just say a little bit about the way this thing works. So this is the periodic orbit continuation theory of Alexander et al., which basically is what makes the whole thing work. So early works go back to the Fuller index, and which is also related to optimal control, actually. But anyway, the idea is you want to study the connected components of periodic orbits in x mu tau space, where tau is the periodic orbit. And there are various ways of doing this, studied by the various people that I mentioned here. And the big problem, as I say, is to prove periodic orbit existence. And for that, you basically need, in all this work, a priori upper bounds on the periods of the periodic orbits. And the trouble is there are few techniques for obtaining bounds on these orbits. So what I showed in this work with Matt Kvalheim is that there's this one form satisfying certain priorities, which satisfies certain properties, which enables a priori upper bounds to be replaced with conditions on this one form. And that's what enabled us to sort of prove existence for the Sprott oscillator. And let me just give you an idea of how you think about this. So I'll just show you a couple of pictures in the remaining time. So this was the rather brilliant idea of York and Alligood and so on, is to have a picture of these periodic orbits. So the idea is that you look at the periodic orbits in space. So the idea is, let's suppose if you look at the picture on the top of the right-hand part of the page here, you can think of the parameter A as corresponding to my mu. So you have some sort of bifurcation parameter. You change mu or A, and you get a bunch of periodic orbits. And to look at the sort of bifurcation behavior of this, Mallet, Perret, and York and company realized that you don't really need the picture of the periodic orbits. Let's just project it down. So we go to the picture B here at the bottom on the right-hand side, which is just a picture of a set of periodic orbits in XA space. So if you think of X as the configuration space, A is the bifurcation space, you move along this line, that's kind of what they call a snake or something. That's a set of periodic orbits. But the complicated thing is it might not look that nice. So if you look at the picture on the left-hand side, you can see you can actually get bifurcations in orbit space. So when you move along, you might suddenly move onto some other branch and that you've no longer got the periodic orbit. So that's sort of what you have to worry about. And that's what they did worry about. And that brings us to the set of so-called generic and non-generic families. So let me just describe that just in the last bit of time here. So here is a kind of, so you can think of generic and non-generic, you get various types of bifurcation in orbit space. So this is just a schematic picture of the kind of thing you can get as you change mu in our case. You can sort of move along. So this is supposed to be a picture of periodic orbits. You move along the periodic orbits. And as you move, you might still get periodic orbits, or you might bifurcate to some other strange behavior. You might get period doubling, for example, just like we get in chaos theory, and you might actually end up with chaos. I mean, we don't know. And that's the sort of thing that you have to worry about. And these are the three types. So going back to the rather brilliant work of Sotomayor back in Brazil. So what he came up with these three types of basic sort of bifurcations you can get in these periodic orbits. So the simplest case being type 0 on the left, then there's type 1 and type 2. And the nice thing is basically these just depend on the Floch A multiplier. So just to put it to mathematics, what I just described here is what you do is you introduce an equivalence relation on the subset of periodic orbits. So 2 points x mu and y nu are equivalent if they lie on the same periodic orbit, and then I project it down. So that's exactly what that picture was. And then I want to look at that set. So there's a sort of a reduction in a sense that we often talk about in mechanics. And the three types of orbits that I've just shown you here are the sort of type 0 orbit, where there are no flock A multipliers that are roots of unity. And so it really makes sense, as I mentioned earlier. So the sort of easy cases where all the multipliers are either inside or outside the unit circle. As soon as you have multipliers on the unit circle, which is sort of like for a regular dynamical system having eigenvalues that are 0, things are more complicated. So a type 1 orbit has a single algebraically simple flock A multiplier equal to +1, and no other multipliers which are roots of unity. And there's also a condition on the speed of the eigenvalue crossing the unit circle. So it has to cross with non-zero velocity. And then there's a final type 2 orbit. So that's the case where there's a single flock A multiplier equal to -1, no other multipliers which are roots of unity. And this flock A multiplier crosses the unit circle again with non-zero velocity. And then, so those are the basic types. And then there's the idea of what are called curves that are, you can get curves that are oriented or not oriented when you look at them. So you can get curves that twist around, and that plays a role in our work too. So I won't worry about that here, but basically what you can show, so once you've got these three types, so let me not give more of the technical details here, but once you've got these three types, you ask, whether your system is one of those three types or not. It turns out, in fact, that the systems that we care about, the Sprott system and the repressolator, are not one of those three types. But again, you can make a sort of continuation. You can look at our system as limits of these three types, and that enables you to use the analysis for these three types to prove the existence of periodic orbits. And so just to sort of end here, so I'll just skip to the end, is basically what you can show is that you can apply this analysis, you can prove a result in general with this form showing the existence of periodic orbits, but moreover, you can do what I did earlier. So if you go back to the Sprott system, so remember we had these Hopf bifurcations which showed us the local existence of periodic orbits. You can actually do better using this continuation theory. You can show that there's a nice set, in fact, it's a really big set. If you look at theorem 12 here, that for all mu between -0.25 and +0.5, F mu has a periodic orbit contained in that set, K mu, this compact set containing all invariant sets. So what you can do with this is show there's a big set of systems that have a periodic orbit, and that explains those sort of simulations that I showed you earlier. You can choose virtually any value of mu, and you get these beautiful, nice, robust oscillations, both for the Sprott system, which I just showed you here, and you can do the same analysis for the repressolator as well. And then you can ask questions about, can you extend it to other graphs? Is it controllable? Can you change the period and so on? And basically what you need in some sense for a general graph is that that it contains something like a cyclic orbit as well, that you should have a circle of periodic, a circle of points, so to speak, something like this circulant structure embedded inside the graph. Okay, so that's it then. So that's all I have to say. Thanks very much for the opportunity to talk. And I'll be happy to take questions or let Leo show us his picture simulation. Thank you. So maybe I think I'll unshare now, right?
Yeah.
So let me just do that. So
thank you, Tony, for the really nice talk. There is a question in the chat or listen. Are these three types of periodic orbits all possible type? Is that just for dimension 3 or any dimension? Could you have multiple clocked multipliers, 1 or -1, or other roots of unity? Maybe the chat appears in the QA tab.
Yeah, no, I can see. Right. So those are, so these are the basic types. So basically you can get those other conditions. So what you have to show somehow is that you continue the system. So for those three systems, there's a way of proving very nicely you get the existence of periodic orbits for a range of parameters. If you have another system, which is in fact what we have, you can show that the system is closely related to those three systems. So those are like the building blocks and you can show there's a sort of nice, you can show that if you can show that the system you want is a limit in a specific sense of those other systems, you can also show the existence of periodic orbits. So yeah, you can get, I mean, you can get really complicated behavior in general. And yeah, and then the second question is there's a reference. So yeah, we did post, there's a paper on the archive, and it just appeared also in the Journal of Differential Equations. And so the introduction describes, both what we did, and there's all the references that I showed here are in the introduction. So I think we provided a nice list of the references to all these different things, actually.
And I have a quick question also.
Okay.
This Sprott system is non-Hamiltonian, non-Poisson, right?
Correct.
So, and we just exhibit a periodic motion that is good because it is dissipative also. Do you know if there is, this is because I don't know too much about the topic, but is there some relation with metriplectic systems? Or in order to find a geometric mechanic way to understand the system?
No, so yeah, so we've tried, yeah, so, you might think that as well. So, I mean, there is a little bit in the sense that, there is the sort of dissipated behavior. So the simplest dynamics without the interconnection, it's just x dot equals minus x. It couldn't be simpler. But yeah, so but as far as I know, that it doesn't, so that's, I did sort of try that as well. You might think, is there a kind of nice double bracket structure or some nice kind of dissipative structure? And it's not, it doesn't seem to be the case. So somehow these repressor systems are they're sort of strongly non-Hamiltonian in some sense, and they're not sort of gradient-like either. They sort of fall in between, and I think that what makes them work in some sense. So it's sort of intrinsic to the sort of biological behavior. But there might be some other structure. I mean, I tried, for example, I also tried to see if there was an example. Can you write, and this is an open question, can you write such a system on a manifold, you might ask, right? So this is on R3, and I haven't sort of given up on that. So there might be some nice structure, so by the way, if you go to, so one of the other interesting things is, so in 2 dimensions, if I restrict it to 2 dimensions, it is Hamiltonian, by the way, so actually Hamiltonian. So 3 dimensions, unfortunately, you might have thought, well, maybe it's Lie Poisson or something, but it isn't. And the other odd thing is that you only get these oscillations in odd dimensions. So you get it in 2 dimensions, it's just stable or not. You get oscillations in 3, 5, 7, 9, and so on. And I think it's somehow related geometrically to the fact that it's not Hamiltonian or gradient. I mean, obviously it can't be gradient because it's periodic in some sense, but it's not Hamiltonian either.
And my other question is, do you think that did you get some range of the bifurcation parameters at the end, or this is related with learning stuff? If one can, for the Sprott system, learn the bifurcation parameter for non-periodic orbits, or to learn limit cycles, etc.
Yeah, that's a good question. I don't know. Now, I think one could certainly think about those things. Yeah, so as I said, these are very simple systems, and that question could be applied to more complicated graphs as well. So yeah, so we came up with this range of parameters, but we don't even know if that's the full range, but at least we can show that for given mu, it works. But yeah, you could certainly try and, I think for a complicated network, it would be a great thing to try and learn, the parameters that make it oscillate and work. Yeah.
Thank you, Tony. I don't know if someone else has any other question or comment. Well, let's thank the speaker. Thank you, Tony, for this nice talk. And thanks to all, we finished the session with this talk, and I wish to thank all the speakers of both sessions of this parallel session on stability of dynamical systems and applications. That's the end of the conference, I guess. It's in a couple of minutes. I don't know if Ayman wants to say something.
Thank you all, and Leo, we want to see the video. We have time now.
I can show the video in order that you can better understand what I wanted to say.
Yeah.
So maybe it was I did wrong. Don't show the video at the beginning and show the video at the end. Okay. You can see the screen now. Now, this is a video that we did with my collaborators, Thomas Beckers from University of Pennsylvania, and Sandra Hirsch from Technical University of Munich to explain our work in a couple of minutes. This is how we apply the technique. It's called that non-dynamics doesn't allow us to reach the cell formation, and how Gaussian processes can learn to set forces online and reach the desired shape. You can see from the picture on the left, with the online learning, the shape becomes more and more accurate. Side shape relations to visualization. Thank you for the extra time. If you have questions, I will be happy to answer about relations of Japanese stuff with machine learning techniques. So thank you, David, Sheiko, Peter,
In this
Silvi,
week,
and Carlos.
we will discuss the formation control problem. Formation control problem can be characterized as.
And see you soon. Thank you.
Thank you all.